All right, everybody, let's go ahead and get started here again this afternoon. And what we're going to be talking about the rest of the day is some inter-AS MPLS VPN scenarios along with carrier supporting carrier. Okay, so up to this point, the stuff that we took a look at yesterday and today, running LDP in the core and running RSVP for traffic engineering, was for running MPLS VPNs within one BGP autonomous system. Okay, so today we're going to look at what happens when you try to span these VPNs between multiple BGP autonomous systems. Okay, now since service providers don't necessarily have points of presence in all the physical locations that their customers are located, we need to figure out a way that if a customer is in New York and it's attached to service provider 1, and a customer is in LA and it's attached to service provider 2, that these service providers can still transport an MPLS VPN end-to-end between these sites. Okay, there's a couple different designs we're going to go through, and the main difference of them is going to be the type of considerations that the service provider is thinking about. So how much control the service provider has over its routing policy, and how much internal information about its own network does it want to exchange with other service providers. Okay, now when we see this, we could technically go ahead and just run LDP or TDP end-to-end between service provider networks, but since those are used specifically for IGP-bound labels, that's typically not going to be a feasible operation, okay, because service providers are not going to want to share their entire IGP topology with another service provider in order just to exchange MPLS VPN information. Okay, technically, we could also use RSVP to provide inter-AS MPLS VPNs, but the disadvantage of this is that we would have to have a full mesh of tunnels between all of the provider edge routers. Okay, now, when Brian Dennis was going through the example of doing the MPLS VPN based solely on RSVP, we saw that on router 3 and router 6, we had to configure tunnels statically connecting each other in order to provide that end-to-end label switch path. Now, as you can imagine, if we have 100 different provider edge routers in various networks that need to build label switch paths to each other, it's not going to be very feasible to build 100 different tunnel or 99 different tunnels on every single provider edge router to build a full mesh of label switch paths with everyone else. Okay, so what we're going to see typically, if the service providers want to exchange end-to-end label switch paths, we're going to be doing that with BGP. Because typically internet service providers already are running BGP with their peers, so it's not going to be a big design change in order to go ahead and run MPLS VPNs on top of those. Okay, so we can see here the topology we're going to be referencing for a couple different designs. We have router 7 and router 8. They're still going to be our customer edge routers, and they're trying to gain transit between each other, but we see router 7 is attached to a different BGP autonomous system than router 8 is. Okay, so first off, we have our basic layer 2 topology already built. We have basic interior gateway routing within the individual autonomous systems. Then we're going to configure BGP and build the end-to-end inter-AS MPLS VPNs between VPN A site in AS123 and the VPN A site in AS456. Okay, now there's going to be 3 different main variations of designs that we're going to see for inter-AS MPLS. The first one is called back-to-back VRF exchange, which is basically when the service providers treat each other as just another customer site that is attached to the VPN. Okay, so they're not exchanging MPLS information between each other. They're just running the VRF directly on the interface, connecting those neighbors, and they're running either BGP or an IGP or even static routing in order to exchange routing information within that VRF. Okay, so we're going to be running PE to CE routing protocols, where in our case technically it's going to be a PE to PE link, but there is not going to be any label exchange between the neighbors. Okay, so they're not going to be running LDP with each other. They're not going to be running RSVP or BGP for label exchange. Okay, the next variation we're going to look at is when the border routers of the service providers peer VPN v4 BGP with each other. Okay, so this is going to be single hop VPN v4 exchange. So we're going to see, depending on how many sites there are within the individual service provider, this may or may not be a scalable option because everyone is going to have to peer VPN v4 with the border routers that connect the different service provider networks. A last variation we're going to look at is multi-hop VPN v4 BGP exchange, and this is where directly the provider edge routers that are serving that VRF, servicing that VPN, are going to peer using BGP VPN v4. Okay, so in our first example here, what we're going to do between router 2 and router 4, we're going to have separate sub-interfaces based on the separate VPNs that we have configured inside the SP networks. Okay, so if we have 10 different VPNs that we want to exchange information, we're going to have 10 different sub-interfaces. So they'll all have separate IP addresses, and we're going to run separate instances of our PE to CE routing protocols on those links. Okay, so depending on how many VPNs we have, this could be a design consideration that the service provider would need to take into account. Okay, so if we have 100 VPNs, we may not want to run 100 instances of RIP version 2 on that individual PE router. Okay, the next variation we're going to look at router 2 and router 4, which are the border routers for their BGP autonomous systems. They are going to do VPN v4 exchange. Okay, what this is going to imply is that, let me bring up the whiteboard here. Let's say that router 3 here, it's learning a route from router 7 inside the VRF. Okay, so we're running a PE to CE protocol here on the link between router 3 and router 7. Okay, router 3 is going to take this update, advertise it into VPN v4 BGP, and pass it on to router 2. Okay, so router 2 and router 3, they are going to be VPN v4 peers in BGP. Router 2 is going to take this update and go ahead and pass it on to router 4 via VPN v4, and then 4 is going to pass it on to 6. Okay, so again, in this same type of design, if we have a lot of VPNs in the network, this may not be as scalable because router 2 and router 4 would have to maintain VPN v4 peerings with all the provider edge routers in their particular network. A last variation we're going to look at is going to be a direct VPN peering between router 3 and router 6. Okay, so in this case, the routers that have that VRF directly attached, they are exchanging the information directly. Okay, this is going to be similar to the previous setup we saw yesterday, but instead of the information transiting just one BGP autonomous system, it's going to be transiting 2 autonomous systems. So we have router 3 and router 6, they're in different BGP ASs. Okay, so there's some additional considerations that we're going to have in order to build an end-to-end label switch path between these 2 routers. Okay, so first thing that we're going to do, let's go ahead and look at the command line and make sure that we have basic layer 2 and layer 3 reachability within inside these BGP autonomous systems, and that router 3 is correctly communicating with router 7, and router 6 is correctly communicating with router 8. Okay, so as the PE to CE protocol between these neighbors, we'll go ahead and just run RIP version 2. Okay, now any of the variations that Brian Dennis was going over earlier, those would be valid options as well. Okay, we could run OSPF, we could run BGP, we could run EIGRP, whatever those individual service providers want to support on their PE to CE links. Okay, so let's go ahead and take a look at the command line here, and we'll look at router 1. What we should see on router 1 . Okay, does everybody see my secure CRT screen here? let me restart it here. Okay, also, if you want to follow along with the slides, you can take a look in the file sharing box there. You should see a link to the inter-AS MPLS VPN slides that we're going to go through. Okay, so let me open up my secure CRT window again. Okay, so let's start on router 1, and inside these service provider networks, we're going to be running OSPF as the IGP. So whether we were running OSPF or IS to IS, it's not going to make any difference as long as we can use that IGP transport in order to build our IGP transport label. Okay, so within the autonomous systems, we're going to be running either LDP or TDP. Technically, we could run RSVP like Brian was showing to build a label switch path based on traffic engineering, but we're going to be running either LDP or TDP, and then between the autonomous systems, we're going to be exchanging MPLS information with BGP. Okay, so on router 1 here, if we say show IP OSPF neighbors, okay, we see we're adjacent with 2 and 3. If we look at our routing table here, we see we have the routes to router 2 and 3's loopbacks. If we look at the show MPLS LDP neighbor output, okay, we can see in this case we're running LDP on the interfaces and we're adjacent with router 3 and router 2. Okay, so if we look at our forwarding table, we should see an end-to-end label switch path between router 3 and router 2. So if we go up to router 3, we'll say show MPLS forwarding table. And we see in order to get to the connected networks on router 1, which is going to be either router 1's loopback or the transit link between router 1 and 2, we are going to perform the PHP process. Okay, so when we're sending them MPLS packets, we're not going to send them as tagged. Or at least we're going to take the topmost tag off of the stack. Okay, there could be other labels underneath there if we were doing VPN exchange with router 1 or if we were doing traffic engineering. And then we can see as we go over to router 2, in order to get to router 2's loopback, we're going to send the traffic out as 23. So if we look at router 1, we should see incoming traffic with 23 is destined to router 2's loopback. So if we show MPLS forwarding table, we see if it comes in as 23, we're going to pop the topmost label and then forward it out the ATM link over to router 2. Okay, so this is the correct output we should see. Now if we look at router 3, we can test this. We'll go ahead and do a trace route. We'll do an extended trace route. We'll just press enter. We'll say we want to go to 150.1.3 or 2.2. We're sourcing it from our own loopback. Okay, the reason we're testing its source from our own loopback is when we configure a BGP peering between these neighbors, we're going to use our loopback interfaces to make sure that router 1 does not accidentally remove the label before it should. Okay, so we want to test transport between router 3's loopback and router 2's loopback. This should be a label switch path. And as we can see, as it goes out to the network, it is being tagged with label 23. And if we debugged MPLS packets on router 1, we should see this traffic coming in as 23 and then going out as an unlabeled path. Okay, now let's go ahead and take a look at the other side of the network. On router 5, we'll say show IP OSPF neighbors. Okay, we're adjacent with router 4 and router 6. So if we look at our routing table, we have the loopbacks of router 4 and 6. If we look at the MPLS forwarding table, we can see that we're popping tags for both of these destinations. Okay, this is because router 5 is directly connected to both router 4 and router 6. Okay, if we look at router 4, we should see the outgoing label for 150.1.6.6 is 17. Because that's the label that router 5 is propagating towards router 4. So if we show MPLS forwarding table, we should see an outgoing value of 17. Okay, which we do. Okay, so if we go ahead and trace, we'll trace to 150.1.6.6. We're going to source it from our own loopback. So we can see, as we expected, as it went out of router 3's link, or router 6's link over to router 5, it was tagged with 17. Okay, when router 5 gets it, we saw that if we did the debug, we would see that it would remove the label and then forward the traffic over to router 6. Okay, so this is the first thing that we always want to verify before we start getting into any more complicated configuration. Okay, like Brian Dennis was showing earlier, you need to make sure that you're building the network in a structured fashion. So first off, test our basic layer 2 connectivity. Okay, then look at our layer 3 routing. Make sure that we have reachability and the correct routes installed in the routing table. Okay, only once the IGP network is built can we put LDP or TDP on top of it in order to build our IGP-based labels. Okay, once we have the LDP or TDP domain built, then we can go ahead and exchange label information with other autonomous systems. Okay, so on router 3 and router 6, we're going to go ahead and configure our VRFs, and then we're going to run RIP version 2 with router 7 and router 8. Okay, so first off, we'll start on router 7. We'll go ahead and run the RIP process. We'll say router RIP, or IP routing first. Router RIP version 2. No auto summary. And all our interfaces are going to be in the 10 network. Okay, same configuration on router 7. Enable IP routing. Router RIP version 2, no auto summary, network 10.0.0.0. Okay, so on router 3, we'll go ahead and configure our VRF. Okay, this is assuming, actually before we do this, we should probably just test basic reachability. Okay, which we do have. 3 can reach router 7. And 6 can reach router 8. Okay, so in global configuration, we'll say IPVRF. This is going to be VPN-A. Now we need to choose our route distinguisher, which is going to make our prefixes unique again. And we need to define the route target. Okay, now the route target here, sometimes it's going to be globally significant, sometimes it's not. It depends on how we are exchanging the inter-AS information. Okay, so what we're going to do here, we'll base it off of the router ID of the router so we can see exactly where it is being originated from. Okay, so we'll say our route distinguisher here is going to be 150.1.3.3. And then I'll say after this, 150.1.3.3, I'll say 123 to match our BGP autonomous system number. Okay, we'll do the same with our route targets. As we export this information into BGP, we're going to export it as 150.1.3.3:123. Okay, now on our interface attached to router 7, which is going to be Ethernet 00, we'll go ahead and apply the VRF, so IPVRF forwarding VPN-A. We can see it removes the IP address, so we're going to go ahead and put that back. Then we'll run our IGP process, so router RIP. This is going to be for address family IPv4 VRF VPN-A. We have network 10, no auto summary, and version 2. Okay, so if we want to do a basic connectivity test, we'll go ahead and ping inside VRF VPN-A now and see if we have reachability to 10.1.37.7, okay, which we do. If we go ahead and look at the routing table for VRF VPN-A, we should see some RIP information coming from router 7. Okay, which we do. So we can see that the VRF-aware RIP process here on router 3 is correctly communicating with the customer edge, which is router 7. Okay, so we'll go ahead and test reachability to this prefix here. It's going to be 10.1.7.7. Okay, now we'll go ahead and do the same thing over to router 6. Okay, let's go ahead and save our config here on router 3. So we'll create our VRF, IPVRF VPN-A. And again, these names are only going to be locally significant. It's the route distinguisher and the route target that is going to determine whether the route is unique and what VPNs or what VRFs it's going to be imported into. Okay, so we'll say our route distinguisher here is going to be 150.1.6.6:456 is the BGP AS number. Okay, we'll say our export route target is going to be the same. So this is when we're taking IGP information and passing it from the VRF into BGP. We're going to be using a value of 150.1.6.6:456. And that's going to be the extended community value that we're using in the BGP routes. Okay, now at the interface level, which is gigabit 01, we'll go ahead and apply the VRF, so IPVRF forwarding VPN-A, reapply the IP address, and we can see now we have connectivity inside VPN-A for that directly connected neighbor. Okay, so we'll go ahead and run the RIP process. We'll say router RIP. This is going to be for address family IPv4 VRF VPN-A, version 2, no auto summary, network 10.0.0.0. Okay, so we see we have the RIP routes from router 6, so from router 8. So if we go ahead and ping inside VPN-A, we're going to ping 10.1.8.8, and we do have connectivity. Okay, so at this point, we take a look back at our diagram. Okay, we have basic OSPF reachability within inside routers 1, 2, and 3, and between routers 4, 5, and 6. Then 3 is correctly exchanging RIP version 2 inside VPN-A with router 7, and router 6 is exchanging RIP version 2 with router 8 inside VPN-A as well. Okay, so we haven't enabled any BGP yet, so we're not exchanging those updates with any neighbors. They're just local in the VRF tables of router 3 and router 6. Okay, so the first variation we're going to look at here is the back-to-back VRF exchange. Okay, now we already have the VRF enabled on router 3 and router 6, and we are already running IGP with router 7, and we're running IGP with router 8. Okay, so what we're going to do, we're going to take these IGP learned routes on router 5, redistribute them into BGP, into VPN v4 BGP, and we're going to pass them onto our border router, which is router 2. Okay, once router 2 gets them, it is going to redistribute them from BGP back into IGP and advertise them as IGP routes over to router 4. Okay, so from router 2's perspective, router 4 is going to look like any other customer edge device. So it's not exchanging MPLS information with it, it's exchanging just a regular IGP update. Okay, so we're going to be running VRF-aware protocols between these neighbors. We could run RIP or EHRP, OSPF, whatever we want to. Okay, we could also exchange it via BGP. Now, once router 4 gets this update, it's going to redistribute it into VPN v4, advertise it up to router 6, and 6 is going to take it from BGP back into IGP for its final advertisement onto router 8. Okay, so this is going to be a bidirectional process. So first thing we're going to do, let's go ahead and set up our multi-protocol BGP peerings between 2 and 3 and 4 and 6. Okay, so on router 6 here, we are going to be running router BGP 456. Okay, and we are not going to run the IP version 4 unicast address family by default. So we'll say no BGP default IPv4 unicast. If we want to exchange IPv4 unicast updates, we're going to have to manually activate that under the IPv4 unicast address family. Okay, so we're going to be peering with router 4 here, who is in AS 456. We'll source this traffic from our loopback. And again, the reason why we're using our loopbacks is that if we use the directly connected links, so if on router 6, if we used our Ethernet, and on router 4 we use the frame relay link, then router 5 would be seeing the VPN tagged traffic instead of the IGP transport label in the transit path. Okay, so we need to make sure that we're peering with something that is not directly connected to router 5. Okay, so we have our basic peer there. We're going to activate this for VPN v4. A neighbor 150.1.4.4 activate. Okay, then the same thing back on router 4. BGP 456. We're not running IPv4 unicast. We're going to be running VPN v4. So we'll say for this neighbor, router 6, updates are coming from our loopback. Okay, we're going to activate them inside VPN v4 activate. Okay, so we'll leave this peering. We'll go over to AS123. We'll peer between router 2 and 3, and then we'll go ahead and verify that these adjacencies are up between the neighbors. Okay, so we're going to run BGP 123 here. Okay, 2 is going to be peering with, actually first let's say no BGP default IPv4 unicast. Now technically we don't necessarily need to do this, but in a real service provider network you would want to go ahead and limit your specific address families, because if we had a full internet routing table here somewhere being exchanged, and these neighbors didn't have destinations that were, or actually sources I should say, sources that are sending to internet destinations, then there's no reason that they should have the internet routing table installed in them. Okay, so unless they have people attached that are sending IPv4 unicast packets, we wouldn't want them to have those routes, because it's going to be a lot of unnecessary resources that we're using up on those neighbors. Okay, so we'll see, we're going to peer with, we'll say neighbor 150.1.2.2. Okay, there's a question here. Can I go over real quick why not to use an IP address that's connected to router 5 for router 6 BGP peering? Okay, let's take a look at this in the context between router 2 and router 3 here. Okay, we're on router 2. We're going to configure our peering statement over to router 3. If we look at our routing table, at this point there's basically 2 different addresses that we can choose to peer with. We can either peer with 150.1.3.3, or we could peer with 150.1.13.3. Okay, both of those are links that are attached to router 3. Now let's say, for example, that we peer with 150.1.13.3. When we go ahead to send a packet to this destination, okay, when we do a routing lookup on this, we say show IP route 150.1.13.3. Okay, we know this via OSPF out the ATM interface. If we look at the ATM interface, so show run interface ATM30, we see that it is running MPLS. Okay, so now what we need to do, instead of looking at the regular IP routing table for our routing information, we're going to look at the MPLS label forwarding information base. Okay, so the router internally is going to say show MPLS forwarding table. How do we get to 150.1.13.3? It says if we want to get to that destination, we're going to remove whatever label we have and send it out the ATM link to router 1. Okay, now let's say in this case that we received a packet that was MPLS labeled. Okay, we saw there, it said the local label was 23. So let's say, for example, that we receive a packet here. Okay, we have our IPv4 packet. And on top of the IP version 4 packet, we have an MPLS label. And in this case, the label would be 23, because that says it's going out towards router 3. Okay, so we have our IPv4 packet. Then on top of it, we have the label of 23. Okay, now in this case, if we removed 23 and sent out the native IP version 4 packet, that's not going to be an issue. Okay, that's not going to be an issue because we know that router 1 has an IGP route to that destination. In fact, that destination is directly connected to router 1, the 150.1.13.0 network. But if this had a label stack, so instead of having just 23, if it had another label here besides 23, okay, so let's say we have a VPN label. We'll say this is VPN 1, or just label V1, and then we have 23 on the top of the stack. Okay, if we go ahead and remove 23 and send the VPN labeled packet over to router 1, what is it going to assume that router 1 needs to know? Router 1 is going to need to know whatever the destination is V1 inside its MPLS forwarding table. Okay, so if we take 23 off and forward the packet onto router 1, that's assuming that router 1 has VPN information about whatever our final destination is. Now, if we look at our diagram, the problem that we run into is that router 1 is not actually going to be running BGP in this case. Okay, so we're not running multi-protocol BGP, we're not running VPN v4, so router 1 is not going to know about the final destinations inside VPN-A. Okay, so we avoid this problem by configuring the peering between the loopback of router 2 and router 3. So when router 2 goes to send the packet out, it is not going to pop the top label. It's going to swap whatever incoming label it has with the outgoing label listed in the MPLS LFIB, and it's going to forward that out to router 1. Okay, there is actually another option that we can do to get around this. Instead of configuring penultimate hot popping, which is going to be the default, we can actually go through a procedure that's called ultimate hot popping. By instead of advertising an implicit null label, we can configure the devices to advertise an explicit null label. And we'll talk about that tomorrow morning when we get into quality of service. It's most commonly used in quality of service in order to maintain an end-to-end diff-serve policy based on MPLS experimental bits. Okay, but for our case, majority of the time you want to make sure that you're peering with some address that is not directly connected to the neighbor that is the next hop. Okay, so the easiest way to do that is just to make sure you're peering with the loopback address. Okay, so let's go back to the command line here. Okay, we'll go back under the BGP process. Let's see what we have so far under BGP. Okay, so under our BGP process, we're going to peer with router 3 from our loopback. And we're going to activate them under VPN v4. Okay, router 3 is going to do the same thing back. BGP 123, no BGP default, IPv4 unicast. We're going to peer with router 2 from our loopback. and then activate them under VPN v4. Okay, so if we go back to the other side of the network, we'll take a look on router 6, and we'll show IP-BGP VPN v4 all summary, and make sure that our peering relationship with router 4 has been built. Okay, which it has. So we have the peering, but we're not learning any information from them. Okay, if we look at router 3, show IP-BGP VPN v4 all summary. We see we're still negotiating with router 2. Okay, now that we can see the peering is up. Okay, so next thing we're going to do on router 3 and router 6, we're going to take those IGP learn routes that are coming from our VRF neighbors, which are router 7 and router 8, and we're going to redistribute them into multi-protocol BGP. Okay, we're going to redistribute them into BGP, and we're going to make them VPN v4 routes by adding the route distinguisher onto the front of it. Okay, so under BGP, we'll say for the IPv4 VRF VPN A address family, we're going to redistribute RIP. Okay, same thing on router 6. And we'll go ahead and check this locally, make sure that redistribution happens. So we'll say show IP-BGP VPN v4 all. Okay, we see those local routes were redistributed in. Show IP-BGP VPN v4 all. And we see they're redistributed on router 6. Okay, now at this point, if we look at router 2 or we look at router 4, and we say show IP-BGP VPN v4 all, we're not going to see any prefixes installed in the BGP table. Okay, now these routes are being advertised over to router 2 and router 4, but if we recall, BGP's default processing for multi-protocol BGP, it says when I receive a VPN v4 route, I'm going to look at what the route target is on the prefix. If I do not have a matching VPN with that route target as an import target, I'm going to reject the route. Okay, we can get around this by saying no BGP default VPN v4 route target filter. Actually, I'm not sure if that's the syntax. Let's see. It would be no BGP default route target filter. Okay, so if we disable this automatic processing on router 1 or router 2 here, and we look at the VPN table, we should see, actually let's clear the update inbound. Clear IP-BGP VPN unicast 123 inbound. Okay, now we can see that we have the updates installed in the VPN v4 table, but they're not actually going to be installed in any routing table. So if we say show IP route VRF asterisk, okay, we don't actually have these routes installed anywhere. Now with the back-to-back VRF exchange, what we're going to do here is actually configure the VRF on router 2 and router 4, and we're going to apply it to the interface between them. So in this case, technically we don't need to use, under BGP, we don't need to use this command, no BGP default route target filter. Okay, we could leave the default processing on. The reason why is that we are going to say here IPVRF VPNA, and we're going to configure, we'll say our route distinguisher is 150.1.2.2:123, and our import route target is going to be the stuff that is coming from router 3, so 150.1.3.3:123. Okay, this is going to be applied to the Ethernet interface between router 2 and router 4. So we'll say IPVRF forwarding VPNA. Then we'll go ahead and reapply our IP address. Okay, so we can see we have that connected interface installed in the table, in the VRF table, and what we should see here shortly is these BGP updates being installed as well. Let's go ahead and clear the BGP process again. Clear IP BGP VPN v4 unicast from AS123 will request an inbound route refresh from our neighbors in AS123, which is going to be router 3 in this case. Okay, let's try clearing. We'll say clear IP route VRF VPN A asterisk. Okay, so not yet. Let's go ahead and just clear the BGP session completely. Now, in a real service provider environment, this option right here, this would be a very bad idea to do, okay, especially if you're running, if you have the regular internet table installed in the global IP version 4 table. Okay, this is going to destroy the TCP session with all of your neighbors. In the lab environment, it's okay to do it because we're not affecting anything, but in a live network environment, you would want to ask for route refresh, and if it's not updating, then you're just going to have to wait until the next update period is going to be. Okay, so if we sat here and waited, eventually it would be installed in the BGP table. Okay, so let's go ahead and look at the routing table. And now we see those routes installed. Okay, so if we look at the VRF table for VPNA completely, we see we have that connected interface that's going over to router 4, plus we have those BGP routes installed that are coming from router 3. Okay, now on router 4, we're going to do the same thing. We're going to go ahead and create the VRF, so we'll say IP VRF VPN A. Route distinguisher is going to be our loopback, :456. The import route target is going to be what router 6 was exporting as. So 150.1.6.6 :456. Okay, then we're going to apply this to Ethernet 0. So IPVRF forwarding VPN A, and then we'll apply our IP address. Okay, tag switching actually should not be on the interface here, though that was left from a previous configuration. Let me make sure that's off of both of these neighbors. Okay, so no tag switching on the Ethernet, and router 2 as well. Okay, now there is a situation that you would want to run MPLS inside of RF, and we're going to take a look at that later today when we run the different carrier supporting carrier designs. Okay, carrier supporting carrier basically means that like a tier 2 ISP is using a tier 1 ISP for VPN transit. Okay, so in this case, we do not want to be running LDP or TDP between router 2 and router 4. Okay, the only thing that we're going to exchange on this link is going to be IGP updates. Okay, technically we could run BGP inside of VRF and exchange the updates as BGP, but we're going to go ahead and show it as just doing redistribution into IGP. Okay, so on router 4, we'll say show IP route VRF VPN A. And if this is converged, we should see our connected interface plus those BGP updates coming from router 6. Okay, so we see our connected link. If we show IP BGP VPN v4 all, okay, we see we're getting the routes from router 6, but we haven't installed them in the VRF table yet. And we can see that it is associating it with that VRF table because it says this route distinguisher is the default route distinguisher for VPNA. So it means that we should go ahead and install it in that VRF table. The clear IP route VRF VPNA asterisk. Okay, so we don't have it installed. We'll go ahead and just clear the regular BGP peering. Okay, one way that we could have avoided this as well would have been to configure the VRF information on router 4 before we established the VPN peering. Because what happened is that the adjacency came up, 6 is going to send those routes over to router 4, router 4 is going to reject them. It's going to say, I don't have that route target as an import policy, so I do not want you to send me this update. Okay, so if we look at the routing table now, we don't have it yet. Show IP BGP VPN v4 all summary. Okay, we are receiving the updates. Let's just say show IP route VRF VPN A. Okay, we have our connected link. We're saying import routes with 150.1.6.6:456, which should be the right target. Okay, so now they get installed in the table. Okay, so sometimes clearing the VRF table is going to help. Other times you're going to have to either request route refresh in from the BGP neighbor, and if that doesn't work, last case scenario, you would just go ahead and do a hard clear on the BGP session between them. Okay, so drop the TCP session and then rebuild a complete new adjacency between the neighbors. Okay, so now router 2 has routes through BGP. Router 4 has routes through BGP. We're going to run an IGP between these neighbors and do mutual redistribution both ways. So on router 4, we're going to go BGP to IGP. Router 2 is going to receive that as an IGP update and then redistribute it back into multi-protocol BGP. Okay, so in this case, let's go ahead and run OSPF between the neighbors. Okay, so we'll run an OSPF process. We'll say router OSPF 100. This is going to be a VRF instance for VPN A. Say network 150.1.24.4 is going to be in area 0. Okay, we'll say the same thing on router 2. So OSPF 100 is going to be for VPN A. Network 150.1.24.2 is going to be in area 0. Okay, so the neighbor's not up yet. If we look at the show IPOSPF 100 interface brief output, we can see it is running on the link there. Okay, one of the ways we could speed this up would be to change the hello interval between these neighbors. Okay, so if we set the hello interval to something lower, let's go to the interface. We'll say just IPOSPF hello 1. IPOSPF hello 1. Okay, so for VPN A, we have network 150.1.24.2 is in area 0. So let's show IPOSPF interface Fast Ethernet 1.0. A network type is broadcast, area is 0, hello is 1, dead is 4. Okay, let's make sure that this matches on the other side of the link on router 4. So we'll show, let's check the neighbors again. Show IPOSPF neighbors. Okay, now it's listed. Now that's router 5. Okay, so no neighbor yet. Show IPOSPF interface Ethernet 0. Okay, let's make sure, let me ping inside the VRF. Let's ping inside VRF VPN A. Make sure we have reachability to the other end. Okay, we do have reachability there. Let's go ahead and ping the OSPF multicast address. Okay, this is showing us that those updates are getting to router 2, so for some reason they're not establishing adjacency. Okay. What is, oh, you know what it is? Yeah, Brian mentioned this before as well. Let's go ahead and take a look at the issue here under this. Actually, it's on router 2 side. Show run, begin router, OSPF. I had the passive interface command in there earlier. Let's see. All right, I don't want to spend too much time troubleshooting. Let's try it. Let's try a RIP process instead. Router RIP, address family, IPv4, VRF, VPN, A. This will be on the 150 network. Version 2, no auto summary. In router RIP. Okay, let's go ahead between 2 and 4. Let's go ahead and add another interface into the VRF and see if they're exchanging directly between these neighbors. Okay, so let's say interface loopback 1. We'll say 150.1, 44.44, and this is going to be in VPN A. Okay, we'll do the same thing on router 2. IPVRF forwarding, VPN A. IP address 151.22.22/32. Okay, so they're not exchanging RIP updates either. Let's see if this is a layer 2 problem. Let me go over to the switch here and show run interface fast Ethernet 2. It's in VLAN 24. That interface is in VLAN 24. Let's take a look at the spanning tree instance. Show spanning tree VLAN 24. Okay, it's forwarding out both of those links. Let's look at. Okay, so we have connectivity between them. Let's go ahead and debug the RIP process and see if anything is being sent out the interface there. VPR, VPN A. We should be receiving. Let me see. Show IP protocols. Begin RIP. This should show the gateway there. It should show that we're receiving updates from router 4. Let's debug IP RIP. Let's just debug IP RIP. All right, we're trying our last-ditch effort in the troubleshooting process. We're going to go ahead and reload. We'll save our config and reload. Now, don't eliminate reloading from your troubleshooting process, because in this case, the configuration is pretty straightforward. We see that we have basic connectivity between the neighbors, but for some reason, they're not accepting the packets between them. It may have had something to do with the order of operations that I had MPLS on those interfaces first before we applied the VRF. But let's go ahead and try this out and see if that makes any change. Okay, let's go ahead and take a quick 5-minute break while these guys are reloading, and